This conference will now be recorded.
Good morning, everyone. This is Bharani Chandrakumar, and I'm an academic at Geomanist of Technology. So today we'll be discussing about the PID control design and application to DC motor. Uh, this will be an extension of yesterday's discussion. So this is the recap. So yesterday, what we discussed is what is control system, some fundamental aspects of control systems and applications, and how to build a model in MATLAB or Simulink. And then we did the open loop analysis, and that gives us the motivation for the closed loop analysis, closed loop control. And we have simulated of a second order system in open loop and feedback mechanism as well, with closed loop control as well. And more specifically, we were concerned only about the gain control. So in this lectures today's we will discuss about the PID controller, why PID controller is required, and what is its importance for the real life applications are concerned, and the other aspect. And we will, more importantly, we will do the hands-on session, so which will give you the feel of PID controller. So that is the actual purpose of this SDP as well. So this is the fundamental block diagram of the PID controller. If you see here, the PID controller, uh, this is the system. The system can be anything. It can be, which you want to control. So that's what we discussed yesterday. What is the system? And the input of the system is coming output as the output of the PID controller is nothing but input of the system. And the whole purpose of this PID controller is to provide an appropriate control U in such a way that the error between this reference and the output goes to zero. That means the error goes to zero. And I'm saying this is a very naive or the basic PID controller block diagram. This simple block diagram we cannot expect in all the industries or in majority of the industries. There will be several other loops as well, so which I have not shown here. So the name itself says the P means proportional, I means integral, and the D means derivative. So proportional, integral, derivative control. So why the name it has come from? Why we are calling this PID? So the answer is this one. U of t, the output of the PID controller is proportional to the error. You can see that is proportional to the error. So there are three different components here: proportional, integral, and the derivative. So as far as the proportional is concerned, so this deals with only this first term. If I say that if it is the only proportional control, that means u of t, my control input, the control input, or the control input u, which is going to the plant, is directly proportional to the error. And if I equate that one, that proportionality constant is called as a Kp, which is the gain. Once again, this u of t is the control input, which is going to the plant, is directly proportional to this error. I am assuming that the Ki and Kd are zero. Just I am discussing about the Pi control. So the control input is directly proportional to the error, and if I want to equate it, that proportionality constant is nothing but Kp. That is for the P control. When it comes to the I controller, the control input U is directly proportional to the integral of error. So that's why the integral is coming into the picture. Okay. And if I want to remove the proportionality constant, that is Ki. And the third term, you can see that control input, if it is directly proportional to the derivative of the error, we call it as a derivative control. And that proportionality constant, we call it, we name it as Kd. So there are three things here: uh, proportional, integral, and derivative. If we combine all of them together, assuming that Ki is not equal to 0 and Kd is not equal to 0, we call it as PID control. And if you see here, if I take the Laplace transform of this equation in the S domain, so U of S equal to Kp, this E has become E of S, plus you might be aware that if I take the Laplace transform of this integral, it is nothing but 1 by S. So that's why Ki into 1 by S. And similarly, the derivative, if I take the Laplace transform of this derivative terms, that will give us S into Kd into Es. So this whole expression, what you are seeing U of S is the PID control expression U of S in terms of in the S domain, and Kp plus Ki by S plus SKD is called as PID controller in S domain. So this is of much important. So what is unknown here? 1 by S, S is a Laplace operator, so that is fine. You might be aware. E, error you can get it from by this subtracting the reference and the actual output. The things which are missing here are Kp, Ki, and Kd. So these three gains completely dictate the system's performance. So how do you select? Throughout in this lecture, we will see how to select this one by the trial and error methods, by the Naves method, by the Nave approach, and by auto tuning as well. So the three gains which are very much important are proportional, integral, and derivative. We will have the more discussion about these three gains in the coming slides. So this is the fundamental PID controller block diagram. So the proportional control I'm continuing. So when I say only proportional control, what I mean here is I'm only keeping the Kp. The other terms Ki and Kd I am equal to zero. I'm equating it to zero. So what is going to happen in this expression? In this expression, if I substitute Ki and Kd as zero, so these two terms will vanish. So you are only left over with U of t equal to Kp into E of t. So that's what you can see, that U of t equal to Kp into E of t. So the good thing about this one is it improvises the rise time. We have seen what is the rise time yesterday. If we use the proportional controller, it will improvise the rise time. That means it will make your system faster to reach the reference value. The caution here is it can be used if the steady state error is of not major concern or the system has inherent integral action in it. So if you use this proportional control alone, it gives you the faster response, but the problem here is it will not make the steady state error zero. What do you mean by this thing? So if you are using the proportional controller alone, if you want to go if you want the reference speed of 1500 rpm for a DC motor, then everything is fine. The transient response, the rise time is good, the settling time is good, the peak overshoot is good, but this will not give you the steady state error zero. So instead of the 1500, it might give you the constant steady state speed at 1200 or 1600 or 800 or something. So there will be always be a steady state error. However, if the steady state error is not your major concern, you are only you just want your system to be stable. Stable means it let it settle at any time at any speed. Let us assume of 1200 rpm, 1000 rpm. It doesn't matter to you. So if that is the case, then proportional constant is good. Or you can use if the system has inherent integral action in it. So the example what we had taken yesterday, intentionally I have taken that example because it has the inherent integral action in it. What is it? We will see in the coming slides. So the lesson here is the PI controller will not ensure the steady state error goes to zero. So if the steady state error is not your major concern, then just go for it, proportional controller. The second thing is PI control. In the PI controller, what is happening here is Kp and Ki terms will be there. So what is going to happen here? Kd equal to zero. So in this expression, only the first two terms will be there. The third, if I'm equating this Kd equal to zero, so my PID will act as PI because the derivative gain is zero and hence the derivative control will not be activated. So that's what you can see here. Kp into error plus Ki into integral of error. So it has only the proportional Kp and the proportionality constant Ki. It doesn't have the Kd, so Kd equal to zero. The good thing about this PI controller is steady state error. That means if you use proportional control alone, it doesn't have the capability to eliminate the steady state error. However, if you use the PI controller, it eliminates the steady state error. It eliminates it has the capability to eliminate the steady state error. We'll see this one. However, the problem here is if you use only integral, that means only ki instead of this kp equal to 0 is not preferred. So integral action, integral control alone is not preferred. That means u of t equal to ki into this integral term. So that means kp is 0. So that is not preferred, because what that will do is it will sluggish control signal buildup. So it will slow down the control buildup, and hence your response will also be slow. So in general, so that's why we are using the combination of proportional as well as integral. That means Kp and Ki together, and we call it as PI control. So, so it has the benefits of the proportional control. That means improvised rise time and the zero steady state error. So it completely eliminates the steady state error as well. So the benefit. Sorry. So what I mean to say here is, if if I use integral control alone, it will give the sluggish control signal buildup, and hence your response will be slower. So what I am going to do here is I am going to use the PI controller. So it will have the good properties of both. So improvised rise time, from which is coming from this P control, improvised rise time, and the zero steady state error, which is the property of integral action. So if I use the P and I control together, then what is going to happen here is it will have the improvised rise time and zero steady state error. So that is the benefit of the PI control. So the lessons from this particular slide is, if you want the faster response, use the proportional control itself. However, it will not guarantee the steady state error to 0. If you want the improvised rise time as well as the zero steady state error, use the PI control. So we have not yet discussed the derivative control. In the next slide, we are going to discuss about the derivative control. So one such control is PD control. In the PD control, I am assuming that integral term, the integral gain as 0, and hence it will ensure that only the P and D terms will be there. So that's what you can see, that you have to equal to P terms, the Kp is the gain, and Kd is the gain for the derivative. So what it does is it do the linear prediction of future errors. So the derivative control has the capability to predict the future errors, and it improves the closed loop stability. So PD control, the derivative action is there, then it improves the closed loop stability. And the physical realization, generally this, this derivative term should be avoided for the industries. There are two reasons. The first thing is you cannot directly realize the physically this KD. So the approximation physical realization one generally do by using this thing. S is the Laplace operator and tau is the time constant. This time constant is where one can vary from various values for different purposes. In general, we take it as 100, or in some cases 1 by 100 as well, this tau value. So this is a kind of tuning based upon the how faster, how approximate, how good do you want the approximation, that depends upon this one. So one thing you can see that uh, if this tau s plays a crucial role in some particular cases, otherwise you can leave it as 100. And so the good thing about the speedy control is it improves the stability and the faster response. This is very good. However, the main problem here is the derivative control amplifies the noise. So if you use the derivative control alone, if your system has little bit noise, then the noise will be amplified, and uh, and it has some physical realization limitation as well. So in the industries, because in the industries they don't want this noisy term as far as their applications are concerned. However, if your major concern is stability, and you can say that I can filter out by noise by using the low pass filter, then yes, one can go for the PID control. So the PID controller combines the benefits of proportional, that means improvised rise time, integral steady state error to 0, and the derivative improved stability. So if I use all these three controls in tandem, then I will have the benefits of individual controls. So for the proportional control, improvised rise time, integral control, the steady state error will go to zero, and the derivative control, it will have the improvised closed loop stability. So in industries, in all real life applications, 90 to 95% cases are, are only the controllers are basically the PID controllers. And out of the 90 controllers, 90% cases, again 85 to 90% cases, people use only PI control itself. That means the derivative terms, they keep it zero due to the practical limitations of the derivative term what we discussed now. So why the industry uses this PID controller? Because it is very simple to implement as compared to other controllers. You need only two parameters. One is KP and KI, assuming that KD is zero. If you use the PID, then KD. So only three gains are required to implement, the control system. Whereas other controllers need much more complex mechanisms, much more mathematical understanding, and so on. So this is about the PID theory. So what I'm going to do here is, okay, so I will just show you some small things here, small uh, the requirement of PID controller. So how do you find the PID controller? These gains, KP, KI, KD. There are various methods. One such classical method is called as Ziegler-Nichols tuning method. So in the very early 1940s, 1950s, or so on, so Ziegler and Nichols, they have come up with with some kind of formula to find the KPKI KD value. Listen this very carefully how the Ziegler-Nichols tuning works here is. What they do here is they only the proportional, only the gain, proportional gain is connected to the plant in the cascade, and every loop is being removed, and they keep on changing the gain value until you get the oscillatory response. So only the KP proportional gain, the feedback loop is has been broken, has been deactivated. So you keep on changing KP value until you get the oscillator response. Oscillator means kind of sinusoid, and the point at which for which the gain for which you are obtaining this oscillator response is called as critical gain, KCR. K, critical gain, and the oscillations and whatever the frequency of the oscillations, we call it as critical frequency, and the corresponding time as critical time. So based upon this Ziegler-Nichols has proposed several formulae to design KP, KI, KD values based upon this critical gain and the critical time. However, that will give you the first insight of PID controller. However, there are some thumb rules based upon which you can always tune your system to get the desired response. What are the thumb rules? Just now we have seen. If you improve the proportional gain, your rise time will be improved. If you increase the integral gain, the steady state will go to zero. If you increase the derivative gain, the system will have improved stability. So these are the thumb rules, and they can be used for the fine tuning. Once if you get the KP, KI, KD from the Ziegler-Nichols tuning method, it can be further tuned based upon these thumb rules. So so why I have taken the yesterday this plant? You might be surprised that from where this plant has come and what is the importance of this plant. This is the old plant. You can see that this is the old 1 by s into s plus 5. So that is 1 by s square plus 5s. So if you carefully see this particular system dynamic, few things one can observe. The first thing is the order of the system is 2, because the s square, the maximum, s component has s square. So the order is 2. And the type of the system is 1. Type means number of poles at a origin. So you can see that this s equal to 0, if I equate denominator to 0, s equal to 0 is one such pole. So one of the poles is at, one of the poles is at origin. So this is the type 1. So further, if you see carefully, there is an integral action embedded in this one. Integral action is 1 by s. You can see that 1 by s you can separate into two. You can cascade 1 by s and 1 by s plus 5. So two transfer functions. One is only the integral and the another one is 1 by s plus 5. So the system has inherent, integral action in this. So that's why yesterday when we designed only the proportional controller, which is only the gain control, still your steady state error was going to 0. The reason here is because the plant itself has the integral action. So you don't need the PI controller. Only the proportional controller was enough to drive the steady state error to 0. So now the new plant, I assume that my new plant is 1 by s square plus 5s plus 1. Additional one term has come. So as soon as I add this plus one term, then I completely lose the inherent integral action of this plant. So what is the state? There are two poles here. So the poles could be the imaginary. Yeah, it could be the imaginary or it's the real as well. It is the imaginary itself. B square minus 4 is okay, whatever it may be, doesn't matter. So it doesn't have inherent integral action in this one. That means you cannot separate 1 by s into 1 by s into s plus 5, something like that, what you have seen here. So that is a key difference. So this new plant, then we have seen also how to obtain this plant as well. Yesterday we have seen for simple RLC circuit. So today we will see for DC motor as well. How to obtain this plant. The plant is the one which is not in hand. The plant which comes from physical realization of your plant through KVL, KCL, or Newton's laws, or Kirchhoff's laws, or physics, or from chemistry, or from biological relations, or anything. So I assume that we have seen how to obtain this plant as well. I assume that if the plant is in this particular format, then what is going to happen? So this is the one. So I'm revisiting the yesterday's example, the new and old plant with the same control action. You can see that on the right hand side. So this is my old plant, which has the inherent integral action. And this is the response. You can see that it is going from 0, and your steady state error is almost the steady state error is also 0 because the system has inherent integral action here. But if I use the same control law, you can see the same control law, which is the gain of 10, which is proportional gain, and 1 by s square. So you can see that why I am saying it is a proportional, because the error is coming here, E of s. The control law which is going to the plant is U of s. So what is this? This error E of s into 10. So now this is 10 is nothing but your proportional gain. If I use the same proportional gain, you can see most of the things looks okay to me, but the only difficulty here is the steady state error is not 0. That means I want my system to go to 1, but it is settling at 0.9. So the steady state error of 10 you can see. However, here the steady state error is 0 because the inherent integral action. So this is one such help. So what is the lesson here? The lesson here is, if the plant doesn't have integral action in it, then only proportional control will not drive your steady state error to 0. You need some integral action in that one. That is a lesson what we have learned now. And now in the next case, I have replaced this proportional constant or Kp or only the gain block with PID control. And the plant is the same. I will show you how to do this one, and I will send you the YouTube link as well. So this is the PID controller, and 1 by s square, this is the plant. This is the new plant because it has another plus one term, and this is the PID controller. So once if I use the PID controller, my intention is, my desired specification is steady state error should go to 0 in whatever be the case. So I have considered three different cases. The first one is the proportional controller with Kp equal to 10. This is exactly the same what we have seen the results. It is going to 0.9. And the second one is PI controller. What I assume that Kp equal to 10 and Ki equal to 5. And the third one, I have used the PID controller where Kp equal to 10, Ki equal to 5, and Kd equal to 200. How to use these values, where to use, I will show you through the demonstration in another 5 minutes. So I have proportional control, PI controller, and PID controller. So this we have already seen. If I use only this one, the steady state error is not going to zero. There is 10% steady state error. So these are the results. Though this, this looks very tiny, but let me explain you through this one. So how to get the step responses will be this. I will tell you in the last class, but I will just show you the simulations how to get. How can you see in the scope? We are going to see this one. So these are the four time domain specifications parameters: rise time, peak overshoot, settling time, and the steady state error. Let me zoom this one. This is my same plant. If I use the proportional controller, the rise time will be 0.694, peak overshoot is 2.72, and the setting time is 1.72, and the steady state error is 10. How to get this time domain specification? Yesterday we have seen. If it is second order, wherever the maximum you are getting, and the difference between the reference and the maximum in terms of the percentage of the peak overshoot, and whatever the time you are getting, we call it as the peak time. And if the system settles within 2% or 5% of the settling time, steady 2 or 5% of the tolerance band, we call it as settling time. Most probably we discussed only about the 2% only, and the rise time will tell us how fast the system is going. In some cases 0 to 100%. In some cases, in some test group, they say 10 to 90% of the plant output response, the time taken by the plant to go from 10% to 90% of its actual final value. So this is the thing. So what I can see here is, uh, if I use the proportional control alone, see, this is fine. 0.695 rise time is fine. Peak overshoot is, is 2.72, which is fine. Setting time is 1.72, which is very good. That my system is very fast. But this is my major concern. My design specification is I want the steady state error to go to zero. If this is of not the major concern, then for the practical purposes, I will use this one itself, proportional control, because it has a genuinely okay, good rise time. Peak overshoot is less, settling time is less. Only the concern is this steady state error. So for the practical purposes, since I want the steady state error go to zero, I will not use this one. And the second thing is, if I use the proportional integral controls, so this integral action, what it is doing is it is ensuring that the steady state error goes to zero. But there is a trade-off. So what has happened? It has increased the peak overshoot. It has increased the settling time. But since my main aim here is to drive the steady state error is to zero. So this is one such a good candidate, this PI controller. And if I use the PID controller, as I told, the enhanced, improved stability or so on, you can see that the rise time is fast as compared to the other two. Uh, the peak overshoot has a little bit improved as compared to the PI controller. And the settling time has also improved a little bit as compared to the steady state, so as compared to the PI control. And the steady state error is zero. So for the practical purposes, I will go with PI control because there is not much significant difference as far as the rise time is concerned. Only you can see that 0.1 or so, less than 0.1, 0.075 is the improvement in terms of rise time, and the improvement here is approximately 1.4%. Uh, Here you can see that there is improvement of 1.4%, and here also you can see that approximately 0.4 seconds is the settling time improvement. But these are very minute. But the difficulty of implementing the stability control is very is too much, because it amplifies the noise, and physical realization is also difficult, and so on. So for the practical purposes, with little bit trade-off, as a control engineer, I will select this PI controller because it will ensure my steady state error to is zero, and whereas other parameters I kept at a reasonably good values. So I will show you how to build this one. Just give me a second. I will be turning off this screen, because when I open the MATLAB, it will have its conflict. It will slow down the process. Just give me a second. Okay, so now let me share the screen now. I'm ready with some kind of MATLAB analysis. Okay, so the first thing what we will discuss here is with the new plant, how to build a new plant and how to use this gain control. So what I'm going to use here is, since you are familiar with yesterday's plant, this is yesterday's plant, you might be familiar. So what I'm going to do here is this plant need to be changed. So I will double click this one, and what I will do is 150. So 151, I'm going to keep 151. So the constant will also be included now. So see, it is included here, but you cannot see it here because it is very big transfer function, you cannot see here. So now you can see 1 by s square plus 5s plus 5. So this is pretty much clear, right? If it is not clear, I will be giving you the video, you can see. So this is the same thing. So what is happening here is I kept everything is the same, but just in case I will show you the older one, whether it is the same or not. Older plant. So this was my old plant. If I run this one, you can see what is happening. So you can see that with the older plant, this is the response. This is pretty much fine. You can see that this is pretty much going like this. This is settling at 1 because the plant has the integral action. And now as soon as I change this to 1, this is my transfer function. If I run this one, you can see that immediately the good properties of the steady state error, which is going to 0, is no more. So now what is happening here? It is going to 0.91 or so on. So hence approximately 10% is the error in this particular case. So I will tell you how to design the PID controller for this particular one. Next, what you do here is click this browser, Simulink browser, and just type PID. Based upon the which version of MATLAB you are using, there are many such combinations of PIDs you can see here. It is taking its own time. It will take, sometimes few seconds to start with, based upon the how fast your computer, how fast processor you are using. So now let it happen. So I will tell you what is this. So this will act as the proportional controller, only KP, whereas KI and KD terms are 0. But if you want to include the KI and KD terms, the integral and the derivative, so you need to do certain, you can use the directly inbuilt PID controller block. It is still searching for PID controller. It should not take much time, but that's okay. For the first time, if you start the MATLAB and if you're using the newer version, it will take a lot of memory, the RAM usage will be very high. So if your RAM is good, and so that will make the system fast. Though I'm using the 8 GB RAM, i7 processor, but still it is taking because I'm using this GoToMeeting in parallel as well. So that is sometimes, it will slow down the process. So now 76%. 89%, 90. The first time itself it will take time, but then later on for the other examples it will not take much time. 97%. Yeah. So there are lots of PID blocks, so you should choose only the PID controller of PID of S, whatever you can see here. So what you have to do, forget about all this. There for various purposes this PID are there, so which is not of much our interest. So add to the model. So it has come here. So now what I'm going to do here is I will remove this older 10 gain and I will connect. I will use a bit smaller one. Okay. Now, what is this PID controller? What is inside this one? We will see now. If you double click this PID controller, so there will be some default values inside. The default values is proportional gain as 1, integral gain as 1, and the derivative is gain as 0. And this is the filter coefficient, the tau which we have seen. So in the first case, we kept the gain. If you want to use only the proportional gain, proportional control, you set it as 10 and the integral as 0, enter. And if you run, it should give the same control law what you have obtained, same output what you have obtained for kp equal to 10. You can see the same thing you are getting. So now my PID controller block is only acting as a proportional control. So next thing is what I'm going to do here is, instead of this proportional controller, I will use the PI controller. What PI values I have to select? I'll be selecting the kp equal to 10 and ki equal to 5. So I am going to double click this one and 5 and enter. This you can save with another file name like closed loop underscore PID and so on. So now this is, again I will show you what is this thing. The P term is there, integral term is there, derivative term is 0. So now my plant will act as a PI control. So the good properties, you can see that I have not run yet. I didn't run yet. So you can see that, yeah, now it is going to 0.91. Now the steady state error should go to 0. I just ran this one and now you can see the improved response. You can see the steady state error has gone to 0. You can see the steady state error has gone to 0. So as keep on going, so it has almost, it has reached to 1. And if I want to use the derivative control, derivative gain as 200, now what I'm going to do here is I will use the 200 and now I will run this. As soon as if you run this one, you will have different responses as well. So the idea here is you should always, and I will show you the importance of this one as well. Instead of 100, if I use this 1 by 100, the time constant or the filter coefficient, you will get the different response as well. And this is the response what you are getting. So how do you find the peak overshoot? What I told here is, we will see whether whatever I have shown here is fine or not. I will tell you only these two parameters. Here I am saying that if I use the PID controller, the peak overshoot is 12.3. So the maximum value. So if I zoom this one, if I zoom further, you can see that it is 12.3. You can see that 1.123. So if I convert in terms of the percentage and if I remove the one from it, so it is 12.3. And similarly, the settling time is the when it settles within the 2% tolerance response. That means either 0.98 and 1.02 when it is setting. If you want to do that one, you take this area. So you can say that 1.02 when it is coming approximately here, and from then it is almost settled. So approximately you can say that around 3.6 or 3.7 is my settling time. And from here, if you keep on zooming this one, if you just zoom in the x-axis, so you can see that from this particular time 3.5 onwards, the system will be within the tolerance bond. You can see that 1.005 it is not going. So that's why approximately you can see that 3.91 exactly it is coming. So 3.91 is my settling time. So this is what about the PID control design. So the lessons what we learned today here is, the P control alone cannot stabilize the system. Cannot It can stabilize the system, but it cannot make the steady state error to 0. Whereas PI will make it to 0. PID will have the improved transient response. However, if you want further improvement in the steady state, further improvement in the response, you have to use the PID. So PID is better than PI, but PID can be avoided, should be avoided because of the practical reasons. So what I will do here is I will give you these slides. and the videos. I will be giving you 15 to 20 minutes. Let's say now it is the 10:50. At 11:05. At 11:05 we'll meet, and it is only the 5 minutes video, 5 to 7. I think it's 7 minutes video. I'll be sending you the whole process I have explained you, and you have to design the PID controller for this system and try to get the results. So in another couple of minutes, I'll be sending you in the WhatsApp the slides as well as the video. So we'll meet in another, and then after that, we'll meet at 11:05. Meanwhile, if you have any queries, you are welcome to ask.
Sir, Bharani sir. Sir,
Yeah.
sir, this is Appara sir, Venkateshwara College.
Yes,
PI
sir.
and PID compare these two.
Hmm.
Rise time improved or not, sir? PI and PID. Which one is rise time improved?
PI and PID, sir. You can see that
Uh,
PID has improved because 0.556. You can see that here it
less
is
time.
0. Yeah, less time is
Okay.
improved. It is
Sir,
faster.
okay. Okay.
Faster.
Is the less time means it's not the time to stable. It is the time to rising time only. This is.
Yes, yes, it is a rising time only.
If rising time is less, then it is somewhat
It is
problem. Na? I think if rise time
why?
is rise time is should be more. I think because
No, sir. No, 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 sir.
okay,
Yeah,
okay, okay.
yeah.
Not peak or shoot, sir. So that it will
Peak,
slowly rise. It will slowly rise, na? Slowly rising is good or faster rising is good, sir.
sir. If you want to go from one place to another place, you want to go faster or you want to go slower?
Okay,
Which
that
one
is
is the
faster.
better one?
Okay, okay,
Yeah.
faster.
So that's why,
Okay,
sir.
understood, sir. Understood, understood. Okay.
Yeah.
Thank you, sir.
Sir,
Okay,
good
sir.
morning, sir.
Good morning. Good
Sir,
morning.
sir, this is Ramesh Babu from St. Anne's, Chirala, sir.
Yes, sir. Please tell, sir.
Sir, here in the PI controller, in the P controller, if we are increasing
Yeah.
the proportion gain, one side rise time
Yeah.
increases, sir. Other side this peak overshoot decreases, sir.
Yes. Yes.
When we are
Yes.
increasing the KP values, sir, rise time increases,
Yeah.
but at the
Yeah.
same time, peak overshoot also increases, sir.
Yes. So that is called as a trade-off, sir. You cannot have all the good things, by using the simple control. You have to sacrifice something to gain something. So that is called as a
Okay,
trade-off of the control system, sir.
okay, sir. Sir, one more question, sir. What is meant by
Yes, sir.
anti wind up gain, sir?
So when you use the controller integral action, the integral action, what it do here is it saturates sometimes. It gives the saturation in the control gain or saturation in the system's response as well. To avoid that saturation purpose, we generally use the anti wind up controller. So anti wind up, what it will do is it will avoid the saturation. So so in some cases, for the practical purposes, the saturation plays a very crucial role because you cannot change the control gains whatever you want to. Practically, there is some limitation. Even if you're changing the control gains due to the saturations in the plant, it will not see the corresponding response. For example, if you take the this example of DC motor, and in the DC motor, I assume that in the very simple case, the voltage is direct. Sir, please be on mute, sir. In a very simple case, I assume that voltage is directly proportional to the speed. Sir, please be on mute, sir. The person who has just asked the question? Please be on mute. It is echoing. So what is happening here is if we, sir, I'm helpless. Please be on mute.
Sir, I'm on mute, sir. Some other person is unmuted, sir.
Let me see who is unmuted. Hello. Okay. So, arey yaar, this really it is putting me off. If somebody 100 times I'm asking the participants to please be on mute, so it is disturbing not only me to everyone. So, so the problem here is even if the voltage is directly proportional to the speed, due to the inherent nature of the DC motor, or it cannot go beyond the rating values. So if let us assume if the rated speed of a particular DC motor is 1500 and it has designed for let's say another 20% more, let's instead of the 1500 1800. So the thing here is if you keep on increasing the voltage, it will not go beyond the particular beyond a particular speed because of the inherent properties of the plant, inherent capability of the plant. So during those conditions, simply I cannot keep on changing this p value, I value, dk, ki, kp, ki, kd values to get the very faster or to get whatever unrealistic specifications. So you have to be in some cases if I am using the integral, the wind up the saturations will come into the picture. To avoid that one, there is a method called as anti wind up controller as well for the integral to handle with the integral action. So that is my answer. But just give me a minute. I will just first of all I will pass on these slides and the documents to the participants. Then we can have the discussion so that they will start working on that one. Just give me a minute. Just a minute. It is taking a bit time. Just give me a minute. Yeah, I'm ready with the file. The password is the same what we discussed yesterday. It will be Bharani GMRIT through all whatever the slides I'll be sharing with you.
Sir, in WhatsApp, we didn't get anything, sir. In WhatsApp.
No, you'll be getting, sir.
Okay,
Just
okay.
give me a minute.
Okay, sir.
Just in another 20 seconds, it will be there, sir.
Sir, good morning, sir.
Yeah, good morning. Good morning.
Sir, can I ask you doubts?
Yes, please. Yes. Why not? Please introduce
Sir,
yourself, sir, first.
Sir, I am Vamshi Krishna, sir.
From?
Sir, from Anantapur, sir.
Okay. I mean
Sir,
your
how
college,
can
sir.
you
Yeah, sure. That was the rule of the this
yes,
FCDP. Please
sir.
enter so that others should also know you. Yeah. I
Yes,
just
sir, yes.
for the other participant, just I sent the PDF file. Yeah, now you can tell.
Sir, how can you conclude
Yeah, you
that?
can ask now.
Sir,
Yeah.
by looking into the graph, how can you conclude that steady state error 0 or 0.93?
Yeah,
Like that.
Yeah. If the final value, if you have seen yesterday, if the final value is going to 0.9, I want one unit step response I'm seeing. If the final value is going to 1, then I can say that the steady state error is 0. If it is not, then just give me a second. I'm sending the YouTube link and then I will explain you through the demonstration.
Okay, sir.
Just a minute. Because I want to see that the right link I'm sending you. Just
Good morning, sir.
hi, just give me a minute. Just give me a minute, please. Good morning.
Oh,
I'm
okay.
sending you the YouTube link. Just give me a minute.
Okay.
That link what I created was corrupted, so that's why I want to send you the right link. So that's why I'm doing it again. Yes. So now, Kasim, just hold on. I will answer the first participant, Vamsi's question. Vamsi's what he has asked now. For the participants, I have already shared you the YouTube link and the PDF file as well. You can see that one. Vamsi, are you there?
Yes, sir. Yes, sir.
Yeah. Okay.
Yes, sir.
Okay. So let's Oh, okay. Let me share my screen and I will explain you what do you mean by that one. So I'm sharing my screen with you now. Share. I will show you some big plot. Okay, this plot I will show you. Hmm. Okay, so can you see this particular plot, Vamsi? So this is the
Yes, sir.
step
Yes, sir.
response. So from
Okay,
the
sir.
black graph, whatever you have seen there, this can be plotted in a nicer way as well. I will tell you. You can see that this
Okay.
final value here is 1. You can see the final
Yes, sir.
value here, whatever you are seeing has 1. So that means
Yes,
the
sir.
steady state error is 0. That means there is no error when the system reaches the steady state. Steady state means there is no variations here. When the system reaches the
Yes,
steady
sir.
state, you can see that
Yes, sir.
the error is 0. So that's why I can say that the steady state error is 0. And
Yes, sir.
this is the peak. This is the peak. You can see that maximum value, the peak amplitude is 1.12. And 3
Okay,
is
sir.
also there, which is only displayed to till. So that's why my overshoot is 12.3%. So it should go to 1, but it is going to 1.12. So that's why the overshoot is 12%. And the
Okay, sir.
system reaches the settling time 3.91. What I'm saying that from here, you can see that two bands I kept here. So the
Yes, sir.
lower band is 0.98 and the upper band is 1.02. That means 2% of this one. So
Okay,
from
sir.
here onwards, you can see that it is almost in that particular band itself. As soon as the
Okay, sir.
system reaches this band and stays there, the first such instant we call it as the settling time. It should stay
Okay, sir.
from then onwards. Suppose if it is coming here and then it is going like this, we cannot say that it is a settling. The system is settled. So once
Okay, sir.
the point from which it is settled, it is within this band, we call it as settling time. And the rise
Okay,
time
sir.
is, as you know, 90% whenever it is coming from, 10 to 90%, or
Okay, sir.
sometimes 90% also this way. So that is my answer. Yes,
Sir, and
Kasim.
all,
Yeah,
sir,
please.
and
Yeah,
also you, I suggest only PI controller. You said no, sir.
yes, yeah,
But for
yeah.
PID, stability is also there, no, sir. Stability is also an
It is there.
important factor.
It is there. It is there. But when you practically you want to stability, there is not much improvement in this particular case. The example what we have shown, there is not much improvement. But the difficulty here is the practical implication. It will have the noise amplification and other things if you do practical things. So that's why for the
Yes, sir.
practical purposes, we generally avoid PID controller unless there is a requirement. Unless you cannot able to achieve the good stability with PI control alone, then one has to go for the PID control. If you
Okay,
PI
sir.
and PID are giving, the similar response with marginal improvement, then the better thing is to avoid this derivative action.
Okay, sir.
Yes, now I
Thank you,
will.
sir.
I think is it clear, right?
Good
Yes, sir.
morning, sir.
Cleared, sir.
Yeah. Good morning. Good morning, Paul.
Yeah, thank you. My question is with regards to the old plant and the new plant that you gave us. The transfer
Yeah.
function
Yes.
there was 1 over x squared plus 5x for the old plant, and the second one is 1 over s squared plus 5s plus 1. And
Yes. Yes.
from the transfer function, you were able to get, you're able to detect that the old plant had an integral
Yes.
function incorporated in it. So my question is,
Yeah.
how do I understand from the transfer function that this already has an integral plant associated with it?
Okay. So if you can split into like this particular form, that means only the s into some terms, then that means it has the integral in this one. However, in this plant, you cannot directly separate the s term. You cannot write this, in this particular format. Or inherently, it says the type of a system. If the type of a system is one or more than one, that means if the pole, or in other words, what simply you can do here is you can find the poles of this particular trans function or the roots of
Yeah.
this denominator. If you the roots is lying is if one of the root is at 0, that means it has the integral action inherently in it. So that is one such easy way to
Okay.
find this one. Yeah.
So whenever there is a pole that is 0, it already has an integral function inherent in it.
Yes, yes. If you factorize this one, there will be two roots. If one of the roots is at 0, then you can say that it has an integral action in it.
Okay, that's my question, sir. Thank you so much.
Yeah.
Hello, sir.
Yeah.
Sir, good morning, sir.
Good evening. Please introduce about yourself, your
This
name
is
and from where
Niharika
you are. Which? Yeah.
from Hyderabad, sir.
Yeah. Please tell.
Hello.
Yeah. Yeah.
Sir,
Please
you used
continue.
a
Please
filter.
continue.
Why did we use a filter in the PID controller, sir?
Where did we use the PID filter in the PID controller? You mean to say, okay, while implementation, this physical realization, this one? Yeah,
No,
because you
sir.
cannot. Yeah. Where?
When we are implementing in the MATLAB, you used a filter, right? Why did we use that one?
Where did we use the filter? Let me open the MATLAB. This is my MATLAB. So where did we use the filter in this one? I mean,
In the
I'm not bit
PID,
clear. This
in the
block?
parameter. Yes, sir.
In this block. Okay, this is due to the reason what I mentioned here. You can see this one physical for the physical realization. It need to be, you cannot directly implement the what I can say that the derivative term, because it will give you the causal system response, and you don't implement really the causal system. So that's why this is the approximation of this integral thing. So in general, what it will, if you take the integral Laplace transform of this one, it should give you only s into kd. So s into kd implementation is very difficult. So that's why what we are doing here is tau into s plus 1. So if the tau is very, very small, if you take tau as very, very small, then what is going to happen? Very, very small means if tau goes to 0, then this will goes to only s into kd, because this part will go to 0 and there will be 1. For the physical realization, you cannot implement the causal systems and hence the derivative one. So this is the way to realize a particular derivative term. So that is why that is what in the PID controller, this whatever you mean to say that this coefficient is coming to the picture. Yeah, this is the one. And this is the exactly what I am saying. This is exactly what the realization what I shown there. For the practical realization, you cannot implement the derivative term directly. So this is the approximation of that one.
Okay, sir. Thank you.
Yeah.
Good morning, sir.
Good morning.
Hello. Yes, sir.
Yeah,
I
good
am
morning.
Hashwardhan sir from GMIT.
Yeah, please tell.
Sir, I have a question. Sir, if we implement the PID controller in practical way, how the simulation values will significance in that practical system, sir?
It
With what
depends upon
electronics
how
we are
accurate.
going?
Yeah, it depends upon how accurately your model is, and how accurately you are considering all the realistic scenarios like uncertainty and other things. Suppose if this is a very simple model, and if your plant, if you whatever the system is also is exactly the same, then yes, it is going to work. If it is not, then the first thing is you have to implement, before implementing in the real life system, you have to include all the uncertainties here. Suppose if there is an uncertain, this 5, let us assume this implicates the resistance of in a RLC circuit, for example. So the R can vary from, the practical reasons, it can vary from 1 to 10 as well due to some reasons. So what you have to do is you have to keep this 1, you have to see whether the PID control is working or not. You have to keep 10, you have to do all the tests in between 1 to 10, and you have to see if that PID control is working or not. If it is working here, then it will work in the real life systems as well. So you should have thorough knowledge of your system before you do the realistic implementation. If you are if you just simply, if you are taking the very simple plant model for the simulation, and the based upon that simple plant, if you come up with PID controller, and the same thing if you implement in the realistic system, it is not going to work. So before designing, you have to consider all the such kind of realistic uncertainties, realistic saturations, realistic nonlinearities in the plant. Then it is a good chance that it is going to implement whatever, the simulation may work in the real systems as well.
Yeah, okay, sir. Sir, for proportional gain with resistor we can implement, sir, and integral and derivative gains are there, no, sir. For that,
Yeah,
what is the practical hardware model will be there, sir?
it is nothing. It is very simple. If you see integral, you can use the capacitor 1 by c integral of pi dt. If it is
Yeah,
derivative, you can use the inductor L di by dt. So like that, you can do the physical realization. It is as
yeah.
simple as that,
Okay,
my
sir.
friend.
Thank you.
Yeah. Yeah.
Hello.
Yeah, hello.
Hello, sir. This is Ganesh from Bapatla Engineering College, sir.
Yes, please.
Sir, I have a doubt. Just now somebody asked about the realization, physical realization of PID controller. You said that
Yes, yes.
it can be realized by using R, L, and C. Are there
Yeah, yeah.
any alternatives for physical realization, sir?
And nowadays, nobody is using these analog controls. So what are
Of
LC,
course,
what it
of course.
so
Yes.
everything is digital. So in the digital controller, you can realize any such, any such controller very easily. You don't need the physical parameters. So in the digital
Yeah.
controller, just small processor, Arduino or Raspberry Pi, you can simply implement. You can just drop down this code there. So it is very simple now. Nowadays, it becomes very simple.
Okay. Can we
You
go
can
through op-amp based applications, sir?
Yeah, you can go.
Op-amp.
You can use the op amps. You can use the transistors. You can realize the integral. Like
Yes.
LC Colpitts oscillator. What you have, what you have seen in the laboratory. Those are basically can be built with MOSFETs, IGBTs, or transistors as well. So it is
Okay.
possible. But in
Okay.
general, people nowadays no more analog controls. Very
Yeah,
rarely
of
people
course.
use. So
Yes.
that is the thing. Yeah.
Yeah, I know that they can't be realized. The analog are outdated. Yeah, I don't want to know about recent trends, sir. Okay, thank you. Thank you, sir.
Yeah. So the digital controls, Arduino's, Raspberry Pi, ARM processors. These are the standard ones what one can use.
Okay. Okay. Thank you very much.
How many of you have done the simulations? Can you please put it in the chat box? Oh, there are 16 chats. Let me see the questions. How to choose the values of KPK, KD? Yeah, just one such methods I told you is the Nutan has asked how to get this KPK, KD. Yes, you can use by using Ziegler-Nichols tuning method, or by using you can use the auto tuning, which I'll be explaining you in a minute. The derivative control, just we have explained the stability. Most of the messages are good morning. How it significantly, okay, this has already filter in PID parameters. Swami has asked, P controller increase TR, but MP disc. Yeah, there is a trade-off, Ramesh Babu. There is a trade-off between all these things. I think in another 5 minutes we'll start the.
Sir, sir,
Yes, yes.
sir. If I copy the link and paste it in a Word document, then
Ah,
from there itself I cannot open that YouTube link, sir. It's not opening.
why?
In WhatsApp, it is okay, sir. If I click in the WhatsApp link, it is opening the YouTube. But if I copy in the Word,
I think you cannot have copied properly, sir. It should work.
sir?
It should work. You cannot
Okay,
have
okay,
copied
thank you.
properly. It should work, sir. It should work.
Okay, sir, thank you.
Okay, anyone? How many of you have done this one? Jyoti Patra, Prasad Patra has kept something. Okay, he's the new person who has joined. Okay, okay, sir, considered. Good, Harshavardhana, Sridhar, Saurav. Okay, so now we will discuss the PID controller, and then we will see how to design the PID controller for DC. Okay, guys. So let's start our discussion on PID controller of a DC motor. Okay.
Sir.
Yeah. Hello.
Sir, in the result you shown earlier in the workspace, how to draw all the editing, sir, that lines.
Yeah, you can just put the grid, GRID. Grid will give you. It will grid the the complete the picture, GRID. And if you want to see the settling time, rise time, peak overshoot, there is something what you have to do. So which I'll be explaining on the last day. Just I don't want to make the things complex now itself. So in the last day, I will tell you how to automatically get all the time response parameters. Okay, so we are proceeding now as we are running out of the time. So we will now go to this DC motor. Consider this as a DC motor. The reference from this particular Michigan University, I have taken the content. You can go and see that one. So whatever I'm teaching you, it is nothing new. I'm teaching you. So whatever I have learned, just I am passing on to you. So it is nothing that I have invented the wheel. So whatever I have learned from various sources, the source is also been given to you so that you can explore more. I'm just trying to simplify the things, and I'm just collating the things from various platforms and making it simple for your understandings. So that's what I'm doing here. Because in the internet there may be, at least in this DC motor, as soon as you click, there might be at least 1 crore web pages will be there. So but the best one I have selected, and just I'm explaining this one. Consider the DC motor. So this is the DC motor. RL and back EMF, and J is the inertia, and T is the torque, and so on. So what is this? Which type of DC motor is this one? Can anyone can tell? What is this? What is the type of this DC motor? I will give you some hint as well. Torque is
Series type.
Shunt RLC. Series generator, sir.
Series motor, sir.
Wait, sir.
Separately executed, sir.
Separately executed.
Okay, hold on, guys. Okay, so
Separately
my
executed, sir.
yeah.
It is
Okay, fine.
no doubt, sir.
Okay. I'm not going. Armature control or field control?
Sir.
Armature control or field control?
Armature
Based on
control.
control, sir. We can do both.
You see here the field is fixed. So what is this type of?
Sir, armature control. Sir.
Okay. I will leave
Armature
that.
control.
guys, please go in the mute mode, please. Okay.
Okay, sir.
So this torque is directly proportional to the current, and this proportionally constant, I'm calling it as KT. And E is directly proportional to theta dot, where theta dot is the speed, and this proportionally constant is Ke. And system equations, I can write it like this. If I follow the standard KVL KCL, something like that. So L into di by dt plus R into I equal to V, the input voltage, minus this back EMF, which is K into theta, because of this sign, the same signs. So that's why it is coming as a minus. And this is the mechanical, this is the electrical equation, this is the mechanical equation. That's why we call this DC motor as an electromechanical device. Why? Because it has electrical components as well as mechanical component. We can little bit decouple both of them. If you assume this part as 0 and this part as 0, you can decouple the electrical and mechanical, but not completely we can decouple. So that's why it is an electromechanical system, where J into theta double dot, theta is the speed, theta is the displacement, theta dot is the speed, theta double dot is the acceleration, theta double dot plus b theta equal to K into I. So these are the two standard system equations. So from these two standard equations, how to obtain the transfer functions and the state space is of our interest. So this, all of you know that from how you have obtained this equation. This is the first thing, system modeling, what we have seen in the last class, system modeling. So this is called as a system modeling. You have the differential equations, and now I'm going to derive. Now I'll see what is the transfer function, how to get the transfer function from the system equations. So this is the transfer function. Theta dot is my output, V of s is my input. That means speed is my output and voltage is my input. So as far as this motor is concerned, the voltage is my input and the speed is my output. So I want to control the speed of a DC motor. So that's why the output I have taken as the speed, and this is the input. And this is the big transfer function what we have obtained. And this is the state space model as well. So anybody want me to derive this one in 5 minutes? I can do it quickly if you want. Please respond if anybody is interested. Otherwise, I will assume. Hello?
Please do it, sir.
Okay, I will derive this one now manually. Just give me a minute. And it will not take more than 5 minutes. I will derive both the transfer function as well as the other thing as
Sir,
well.
your voice is not audible, sir.
Just a minute, it will be audible now. In a minute, it will be audible now.
Okay, sir.
Something is visible on your screen. Can you see something?
Yes, but it's not so clear.
Can anyone respond? Can you see anything here? Can you see my hand?
Yes, sir, but words are not clear.
Just a minute. Yeah, can any of you can see my screen now? The paper
Sir, the letters
which
are
I'm going
not
to derive
visible,
now.
sir. They are blurring.
Paper is not visible, right?
Yes, sir.
Yes, sir.
Blurred. Totally blurred. What? The letters are not visible.
Now is it visible now?
Yes, sir.
Is okay, sir.
Yes,
Okay.
sir, a little bit better
Okay.
than that.
So you please zoom it, sir. If you zoom it, then you will get it. Now it should be better now maybe. You just keep in the mode, not the view everyone. You can keep in the mode like view the active cameras or who is talking.
Sir, please can you
Yeah.
tilt it 90 degrees counterclockwise because it's horizontal. Make it vertical so that we can see very well. No. Anti-clockwise, sir. Yes.
Now you can see it, right? Is
Yes,
it
sir.
is it better?
Yeah. It's better, sir.
I'm using all the the known technology, whatever I know, to make
Now
the
it is
things
okay.
better. Okay, right? It might be a little bit bad, but please be with me. So I will just explain you. Okay, so let's start the two equations. The first equation is L di by dt equal plus Ri equal to V minus Ke into theta dot. I will consider the first equation. The first equation, if I take the Laplace transform, all of you please be on mute. If I take the Laplace transform, then this di by dt will become S. So S into L plus R into I of S equal to V of S minus, I will, for the time being, I will keep it as theta dot still, because theta dot is the one what I want. So this theta dot I can write it as omega. So what is going to happen, this one minus Ae into omega of S, theta dot equal to omega. So that's what I have written here. So the next one is J theta double dot plus B theta dot equal to K into I. If I take the Laplace transform of this one, since theta double dot is there, it will become S square into J plus B is the constant. Okay. Otherwise, I can write in the other terms as well, J into omega dot, because theta dot is omega, plus B omega equal to K into I. Okay. So this is one equation. So if I take the Laplace transform of this equation, this will become J into S into omega plus V into omega equal to K into I of S. This is one such way of writing the thing. I can write in another way as well if you want, really, in the theta dot and so on. So what is happening now here is, so this is one such thing. So I have to, what I am interested here
Sir,
is theta
here
dot.
we will get omega of S, sir.
Yes, sir. Theta
Omega.
dot is omega. Yeah.
Okay, JS,
So
JS of omega S, we may get.
yeah, fine, sir. I'm just dropping the of S expression here for
Okay.
the simplicity. Okay. So the transfer function, what I'm interested is theta dot of S by V of S, or in other words, omega of S by V of S. So this is I want. So now this equation, if you see this equation and this equation, so what is the things? So everything is fine, but I want to eliminate this current expression. So what I will do is I will take the current expression from here and then I will substitute here and then I will rearrange these things to get the desired equations. So how to do that one is the big question now here. How do I do that one? So anyone, any clue? So now I will more specifically, I will write my system, my equations, the two final Laplace transform equations. I will write it like the first equation I will write SL plus R into I of S equal to V of S minus KE into omega of S. So what will be my I of S here? I of S equal to 1 by SL plus R into V of S minus KE omega of S. Okay, so this is my I of S expression. In the second expression, so what I have to do here is J theta dot plus BS square. So the another equations what I will say here is this. I will write it as a equation. The another equations I will write as J. So the good thing what you have to always remember here is theta dot equal to omega. Okay. So now what I am going to do here is J into omega, J into omega or theta dot, or more specifically I will write it as omega equal to theta dot. So now S square, all of you listen carefully, S square into J theta omega S, theta of S. So this is the Laplace or the inverse Laplace transform. What is going to happen is J double theta. Okay. Or in other words, I can write J S into, so S, this S I will keep it. So S into theta, this I can write as S J into theta dot. So this is one way of writing the thing. So this I will say it is a B. Then my what I can do here is I can use my aim is to eliminate the current, because current is the one which I don't want. So wherever this current expression is there, wherever this current expression you can see, if I substitute this current value here, this you can do it later. If I substitute this that here, and if we rearrange this one, then finally you will be getting theta dot by theta dot of S by V of S. Theta dot of S from where you will be getting? You will be getting from this particular expression. So wherever this S square J omega theta, so wherever you have seen here, S square J theta from our earlier equation, from this particular equation, from these particular equations. So where I will be getting as J into S square plus B of theta equal to K into I of S. Or I can write it as Js square theta as Js into theta dot plus B of theta equal to K into I of S. Or Js of omega plus B equal to, what I can say here is I can write it as Ki of S. And then I will rearrange all these terms to get the desired response. So this is the way to do this thing. But you can do it this one. So just substitute wherever this I of S is there, the corresponding values, and you will be getting this one. This is very standard one what you have seen, but the second one is very much important, how to get the state space model. This you see it very carefully, because this already you might have seen several times. It is nothing but eliminating the current value from this thing. So this you can do it. So the next thing is what I'm going to explain here is the state space model. How do you get the state space model is of much important thing. Otherwise, okay. So some of you have written that personally that they want this detailed explanation. So okay, just give me a minute. I will derive very quickly. DC motor L di by dt plus R I equal to V minus Ke into theta dot. If I take the Laplace transform, this will become Ls into I of S plus R into I of S equal to V of S minus S into KE into theta of S. So what I'm going to do here is, or I of S equal to V minus S KE into theta by Ls plus R. So this Ls plus R has come. So this, we have seen this S into theta is nothing but theta dot, that equal to V minus theta dot into KE by Ls plus R. So this is my I of S expression. Okay. From the second equation, so this is from the first equation. From the second equation, what is going to happen here is J theta double dot plus B theta dot equal to K into I. If I take the Laplace transform of this one, then it will become J S square theta plus BS theta equal to K into I of S. So how can I write here is J S plus B. I'm just taking, what I'm taking is S into theta out. So that equal to K into I of S. So S into theta is nothing but theta dot or the omega. So now what I'll be going to do here is this expressions, in this expression, whatever this I of S you are seeing here, from here I will substitute here. If I substitute here, what it will look like, so this will become JS plus B into theta dot equal to K into V minus theta dot KE by Ls plus R. What I'm interested in this V, and I'm interested in this theta dot. So what I will be now doing here is I will rearrange all these equations. So I will cross multiply these two. I will cross multiply. So this will become Js plus P into Ls plus R into theta dot equal to, so this is Ke. Okay. So this I have cross multiply. This is Kv minus, okay, it is K, I will write it as K only. Kv minus theta dot into K square. So if I rearrange, if I take the K on the other side and if I rearrange, then what is going to happen here is this one, I will take it to the other side. And if I take the theta dot as common, Js plus P into Ls plus R equal to, and again plus K square is also there, because this theta I have taken common. This minus is going to become plus K square equal to A into V. So now what I want, theta dot of S. All of them are S, just I have dropped by this thing. So V of S. So equal to, then what is going to happen? This V I have sent to the other side. So this will become K by JS plus B into Ls plus R plus K square plus R into B will also be coming into the picture. This I can say that this is the one for the derivation of the particular this thing, K square. This is the K square only, not plus RB. So because if I multiply, if I open these terms, then what is going to happen here is K by JL into S square, plus if I take the S common here, then what is going to happen? This JL square plus JR. So this has become JR plus BL plus K square plus RB. So this is the one what you can see. So this is my final transfer function. We'll see what is this one. Okay. So the next one here is the state space model, how to derive the state space model. This is quite straightforward. I will just take a minute. This you can do it. I will anyhow I'll be giving you the slides. So the state space model ABCD. So what it says that x dot equal to ax plus du, y equal to cx plus du. So for deriving the state space model, what I'm interested is the differential equations. So my x has two states. The first state is omega dot and the second state is I. So I will say that x1 and x2 transpose I will say. So x1 equal to theta 1 is my first state and sorry theta dot, and the second state is I. So the equations, the first equations, the two equations, what you can say that j theta double dot plus b theta equal to k into I. This is my first equation, what you have seen. And the second equation is Li dot plus Ri equal to V minus K into theta. All of you see this step is very important. If you are aware till this one, so what I want in this particular form. So x dot equal to, what is that x dot? My x is this theta. So what it is going to happen? D by dt of theta dot and current dot. So this will become d by dt. So this will become theta double dot and this I double dot. So what is going to happen here? Theta dot into I plus some expression into my input. Input is V here, so the V. So how do I write this one? So theta dot is nothing but theta double dot. So from this expression, what I can write here is theta double dot. I can write theta double dot equal to K I. What I'm doing is first I will send this on the other side minus B theta minus B theta. So minus B theta. So this J is there by J by J. Okay. So what is going to happen now here is, now I will follow this particular terms to see what is going to do. So minus B by J theta is there, K by J into I is here. So now I am interested in, I will try to derive this from this one. So what, and the another expression what I can say here is this is one such, and the second one is the current expression. So L I dot plus R I equal to V minus K into theta dot. So what is this I? I is my x2. So this is going to x L x2 dot plus R into I is nothing but x2 equal to V minus K into x1. So why I am saying x1? Because x1 is nothing but my theta dot. So this is one such thing. So now, sorry, this is b theta dot, not b theta. This is b theta dot. So this is b theta dot. Okay. So now what is going to happen here is, so theta double dot, theta double dot equal to, so what is going to happen? Minus b by j theta. So this is minus b by j, it will become minus b by j into theta dot. Okay. Plus k by j into I. So this will be k by j into I. So this is coming from theta double dot. And the next expression here is, this is my x2 dot or I dot. So x2 dot, how I can write? So if I transfer this on the other side, v minus k x1 minus r x2 by L by L by L. But what is my x1 is theta dot and x2 is I dot. So this will be I dot equal to v by L minus k by L into x1 is theta dot minus r by L into x2 is my current. So that's what we have seen. So the same thing, if I substitute here, so I dot, so d by dt of I So it has V by L. So here there is no input term. So in the second term, the voltage is coming. So that's why this will become 1 by S, 1 by L. And this theta dot, whatever theta dot you are seeing here, this will be K by L. And this is multiplied by current. So this will be minus R by L. So now what is going to happen here is, and my Y, my output, since my output is Y equal to theta dot, my output is speed. So how do I write output? Y equal to C into X, right? So this is my theta dot and this is I. There is no control input here. So this is this I will take it as 0. So if I multiply this into this, so this will become 0, the only Y equal to theta dot. So that's why you are getting it. This 0 is 0. So this is, I call it as A, or the system matrix. This I call it as a B, the input matrix. This I call it as a C, the output matrix, and this is the transmission matrix. So this is the way to derive the ABCD matrices. So this is state space model. Anyhow, I'll be giving you this handwritten things as well. So how to derive the transfer function and how to derive the state space model. So this is quite straightforward. Now what I will do here is I will share my screen now. I will stop. Okay. Okay. So now since two models have been obtained to you, so now what I'm going to do here is with the two models, what I'm going to do here is I will be going to derive the PID controller. So this is x dot equal to x plus b, y equal to c. It's the same thing what we had derived. And these are the plant parameters. So first of all, we'll go for the open loop control, J, B, K, and R and L. Because if you see, the unknowns are J here, L, B, R, K. So this, I assume that these are the values which I have taken from the same reference what Michigan University reference, this reference. So the design specification, this is more important. How do I design? So I want, this is the what I am specifying for my particular plant, that the settling time is 0.5, less than 0.5, peak overshoot is less than 5%, and the steady state error is less than 1%. This is what I want. So to happen that one, so this is again the transfer function. So this when I, so there is a small typo here. The typo here is here the RB terms will not come. If you multiply and expand, then this BR, the constants, we can club it here. So you can see that this is the correct expression. So K square is there. When I club it, then this will become K square plus RB. This is the state space model what we have seen. And the first step here is you have to create a parameter file. In the parameter file, you have to save all these values. I will tell you, I will show you how to create this one. And then the open loop, just why I have just I'm verifying the state space model, though it is not required for the current purpose, but later on it is going to be used the state space for the current PID controller. Just I have derived how to get this ABCD matrices. There are many ways. If you know the transfer function in the MATLAB, lots of commands there which will automatically derive TF2SS is the command which we'll discuss in the later. The important things to observe here is this is the very similar to the one what we have seen. The plant, how to write this plant, I will tell you. S square, some constants are there, and this is also constant, second order plant. This is the open loop. When I gave S1 as the input and the output what I am assuming. So this is my step response. You can see that the steady state error is not 0. Why? Because if I'm giving the input as 1, my output should also go to 1. So, but what is happening here is, since I have given 1, it is not going to 1. So what is happening? It is going to 0.1. So what do you mean by this thing? The steady state error is 90%, which I don't want. That means if you want your system to go to at 1000 RPM, it is going only 0.1, 10%, 100 RPM only. So which is not the desired one. So what I will do here is, so that tells us to the requirement of the design to go for the PID controller. And this is the PID controller. When I designed this PID controller, you can see that the everything, my desired specifications has been achieved. You can see that very less than 0.5 seconds. The desired specification is, sorry, less than 0.5, peak overshoot should be less than 1, and steady state error should be less than 1. So that's what you can see here. You can see this particular value, the overshoot is pretty less than 5, and it has settled very fast. And this is the zoomed version. When I zoomed this one in the x-axis, so that here the time is 0 to 10, I have taken only 0 to 1. And you can see that, further you can zoom the y-axis over as well to see that good thing. And this is the such comparison when I'm comparing the open loop and the PID controller. In the open loop, rise time is very large. The peak overshoot is, although here there is no peak overshoot, settling time is 2.5, and but the steady state error is 90. But when I use the PID controller, the rise time is very less, 0.06, very fast. You can see that very fast it has reached to 1. And the peak overshoot is also 4%. That means it is 1.04 or so, something like that. Settling time is 0.4, and the steady state error is 0. Now the question here is, what values of PID I have used? So that is the big question. That is the $100 question. How do I get this PID value? So I will show you with a very simple example how to design the PID controller, how to do the auto tuning. So please bear with me for another 5 to 10 minutes. Sorry, so today's class will be delayed by 10 minutes because I want all of you have to feel of the PID controller design, which is very much important. So just give me a couple of minutes. I will open the corresponding file and I will run this thing. It is opening. It is. So this is very, very important step to design the PID control. In 1 minute, I will show you. It will take only 1 minute for you to design the PID control. Okay, so now we are ready with this PID controller. I am going to share my screen now. Yeah. Now this is the screen what I have shared here is. The only difference between what you have done and what you are seeing here is this DC motor model. So this is the DC motor model. And as I told the parameters, the parameter code, whatever you have seen, you have to open the new file here, the new script file. And here, whatever the values, J values, P, K, L, A, B, C, D matrices, the same thing what we have seen, that you can write it here. Sorry, there is D 2 times has been printed here. So if you run this particular file, file, you save this one. How do you get this one? Go to the new, open the new script file, and here whatever you got, you have type and save with the parameter DC motor model, whatever name you want, you can give it. And if you run this file, it will have all the variables in the workspace. So now what I'm going to do here is, this is the PID controller. So again, so my transfer function, what if you see, is what you have seen that. I will show you this transfer function and side by side. Yeah, you can see that this k, the numerator k is here. S square, the coefficient is j into L, that's the j into L. The second is jr plus bl, so rj plus b, because they are scalars, so it doesn't matter if you multiply a into b or b into a. And the third one is k square plus rb, so that's what you can see, that k square plus rb. So that's what it will create, this transfer function. So if you want to see it in a more larger scale, for some reason I cannot enlarge this one. So this is the one. If you want to see in a very largest view the complete transfer function, then what you have to do is you have to drag this until you get, yeah. Now you can get it. So, but I'm not interested because this is completely, making the things clumsy. So just I will go with small display just to show you that this is the same thing. This why it is representing the gain k. By default it represents y of s because it output, but inside it is k. Okay. So now the how do you get this PID values? The first thing here is to get this PID. I will keep it aside. I will don't do anything, but just I will run this one and I will show you how it is working fine. You can see the same response what I have seen, what you have seen there. But how to do it from the scratch? Just go it here, PID, use the new PID, the standard, add PID block, remove the one which I have designed. You click this one, and now from here the actual design starts. By default, as we are aware that by default it is 1 and 0, and the coefficient is, so there is a small button here, tune. What you have to do here is you press this tune one. As soon as you press this tune button, it will take some few seconds, maybe 30 seconds, to come this auto tuner. So in the auto tuner you can automatically set the desired, you can achieve the desired specifications automatically. I will tell you how to get this one. Just let it work. The only thing is you have to press this. I'm not sure whether I have pressed it correctly or not. Yeah, see, you can see that it is generalizing the plant, and it is auto tuner is will appear very shortly. It takes 30 seconds of time or so. Once it is there, it is quite straightforward. So where in the tuner, what it will show you here is there will be two slider buttons. One is for the transient behavior, and another one is for the kind of steady state behavior. So how fast you want and how aggressive you want, everything, in 1 minute you can do this one. There are many other ways to design this KP, KD value as well. People use the optimization methods like swarm optimization, particle swarm optimization, genetic algorithm, fuzzy logic, and so on, which we will not use. In a simple way, I will show you how to, in 1 minute, you can do that thing. So the tuner will come very soon. So as soon as this tuner will open, yeah. So now the tuner has been open. You can see that it will display. Just you have to wait for some time. Yeah. So this is the one. So the thing here is with this is the block. That means which is inside the block, the default parameters, and this is the tuned one. So with the default parameter, you can get this is the line, but this is not the actual our desired one. What I want is this is the tuned, and the tuned KP is 18, KI is 51, KD is 0.9, and N is 32. And you can see the rise time as well, 0.419, and settling time is 1.5, overshoot is 7, and so on. The other frequency domain specification as well. But our, remember that our settling time, what I want is 0.5. This is far way beyond, and overshoot should be less than 5%. So here you can see that this is the response, and this is the transient behavior, and this is basically, the faster or slower it will take. So now what I'm going to do here is, since the settling time is 1.5, I want much faster, that means lesser settling time. I'll go a bit faster. So these all will change dynamically. You can see that now the settling time is 0.2, which is the desired one, but the overshoot is 10.8. So now what I'm going to do here is, I will change this aggressiveness, I will make it bit less. You can see that dynamically how these values are changing. You just see that settling time and overshoot. So dynamically it is changing, settling time is okay less than 0.5, and overshoot is also less than 5. Yeah, so this is one such response what I want. So you can see that the settling time is 0.35, which is way less than our 0.5, and our overshoot is also less, 4.82, which is less than 5% what we want, and the system steady state error is also 0 because it has almost reached here 1. So this is the corresponding KPK KD value. So this you have to substitute in our block. I don't want to do it manually. I will just place this update button. As soon as I click this update button, so this PID, everything will get, automatically it will be the values whatever you have seen, it has reached here. So the earlier I have not yet ran this one. So the earlier one you can see that, the one what we saw, okay, it is not showing. We have seen that with 10110, it is not giving the desired response. Now I will run this. Now as soon as I ran this one, now you can see that the pretty much behavior. So very fast, you can see that within 1 second, less than 0.5 seconds, something less than 0.43 seconds or so, everything has been settled. So that's what we have seen in the tuner, this tuner value. So 0.35, 4.82. So this is my tuned KP, KI, KD value. So this is called as PID tuning. So this is called as a PID tuning. And this you can pretty much, you can do on your own. Okay, so this is the way to do the PID tuning. So now what I will do here is, so this is what my, so this is the one I have to do. So this is the open loop thing. So open loop is not going to 0.1. And how to select this state space, everything in the video, what I will be sharing, it will be given. And this is the one what I have, obtained the desired specification. And in the open loop, if you run the open loop, you can see that greater than 1 and 0 and everything is not desirable. When I use the PID controller, this is the PID control response. You can see that it is within the desired specific range. So there are two assignments here. The first assignment is whatever, I will share you the videos as well, recorded video in the slide. You have to develop the DC motor PID controller on your own. What I'm saying here is PID controller gains are not unique. That means you may get one PID values, KPK, KD. I may get another set of KPK, KD values. And in both the cases, we will be having we'll be having the same desired performance. So they are not unique. There are thousands or millions of combinations possible. After doing that one, what you have to do here is, if you time permits, you go through this paper. If you search in the Google, you will get it, and try to derive the nonlinear controller, nonlinear DC motor, and derive the PID controller of this. So the first thing is what the assignment is. You have to develop, you have to replicate the things what I have shown. I will be sharing you the videos, hands-on video as well. And the second thing is, if time permits, you have to do this assignment. So that's it from my side. So if you have any queries, please let me know. I will answer a couple of queries and then I will activate the quiz link. Anything? Anyone is having any questions? Let me see. Oh, in the chat box, there are some questions. Voice not audible, not visible. Select the camera active mode. Before running, we need to do tune. Before running the simulation, you have to do the tuning. Yes. Yes, sir. Any students, anyone, any questions you have, any queries? So this is called as a PID tuning method. So though it might look bit difficult for you, but it is not that difficult. You can do. I will giving you the hands-on, the video that you can easily do that one. If not, then I will activate the quiz, and the quiz is, it will be completely based upon this one. So you can do this one, the video, by seeing this one. It will take hardly 10 minutes, and the quiz will be mainly based upon this DC motor PID control design itself. So I'm keeping now this slot open today bit for more time. So by 12:45 till 12:45, I will keep the quiz option. I will sending you the YouTube of. I will be. I'll be. Nelson, could you please be on mute unless you have any query? Okay. So now the quiz will be based upon this PID design itself. So that's why I'm giving you 45 minutes of time from now. So 12:50, something like that, I will close. So I will be sharing you the video. So best thing is, first you do some hands-on on this video, and then if you attempt the quiz, that will be very much easy.
Hello, sir. Hello.
Please tell, please. Hello.
This is Parthiban from Sedamal Engineering College.
Okay.
Sir, what is the difference between transfer function model and state space model? Why do you go for state space rather the transfer function, sir?
Transfer function model and the state space model are the equivalent representation of a system. Transfer function is unique, whereas the state space model are not unique. In some of the cases, if you have to represent the system by using the state space model, because if you want to have the access of all the states, suppose if you have around 10 states, and if you access each of the states, the transfer function model is not possible. It is quite difficult. However, if you're using the state space model, then it is very easy. And the second, transfer function, by the definition, you can only represent the linear system, linear time invariant systems where the initial conditions are zero. If the initial conditions are not zero, you cannot represent it by using the state space model. Another difference is state space model. Any type of system you can represent by using the state space model.
Sir, your
A,
voice is breaking, sir, actually. Hello, sir.
yeah, you please be on mute, sir. Then I think it will be more clear because it is echoing due to some problem. So the another difference here is another such difference here is you transfer function is only applicable for the linear time invariant, whereas any kind of systems you can represent in the state space form. And initial conditions, what you have assumed for the transfer function is zero, but in the realistic condition, initially, suppose if you're using the RLC circuit, initially the inductors and capacitors can be initially charged. You cannot take the initial conditions as zero, so that you cannot represent in terms of transfer function. But state space, it is possible. So that is my answer.
Okay, sir. States in the sense, which are the parameters that is varying with time. That's things we are calling
Yes.
states, right, sir?
Yeah. In the DC motor, there are two states we consider. One is the speed, and the another one is the current.
Okay. Thank you, sir.
Yeah.
Sir, one more doubt,
I
sir.
have. Yeah.
In
Please.
state space model, in output equation, normally we are not getting that D value. So what is the reason for that?
The D is called as a transmission matrix. It generally have the relationship between the output and the input. If you see Y equal to CX plus DU. So the D transmission matrix, if there is a direct relationship or static relationship between the output and input, then only that D will appear. But in general, there will not be much direct static relationship between the output and input. It will be the dynamic equations. That's why it's been suppressed in X dot, not in the Y. So
Okay, sir. But is there any example? If you can you suggest, sir, such equations that D comes? Is there any model, sir? Hello.
Sir, Dr. Barney, sir.
yeah, hello.
Sir,
Yes, sir.
I'm Mr. Apparao from Ankeshwar College. Sir, in today's
Yeah.
DC model, we have used simulation model. We have used transfer function.
Yeah.
Then where will we use the state space model, sir? State space equations.
That's what when you come for the LQR pole placement controller, which I'll be discussing in the next coming classes. There, the state space model
Okay,
will be
okay,
required.
sir. Okay, sir.
To the
Thank
feel
you, sir.
of what is state space model, I have just derived for this one. Yeah.
Okay, sir. Thank you.
Okay, guys, I've sent you the video. I will now be sending the so I'll be sharing you the link as well. Let me share this one. Yeah, the PDF file and the DC motor video has been sent to you. Now I'll be sharing you the quiz as well. So the quiz I will keep it open till 1 o'clock. So, but before that, if you do this PID control exercise, that will be much helpful. Hello, sir. Sir. Hello, sir. Yes, sir. I'm in the boardroom, sir. I'm in boardroom, sir. Boardroom. Just a minute, sir. Is it audible now? Just a minute, sir. You're audible. No, no. Is it audible now, sir? No, no, no. I have not connected through PC. Hello, sir. Is it audible now? Is it audible? Hello? Sir, I am audible? Hi, sir. Am I audible now? Okay, okay. Okay, sir. I'm trying to contact sir. It is not going through. I will call sir again. Sir has joined, sir. Yes, sir. Hello. Hello, sir. Good morning. Good afternoon, sir. Just a minute, sir. I cannot. Hello. Yes, sir. Sorry, sir. There was some issue with going. So, sir, this meeting is regarding is the hosting of international conference, and we have Prem has explored with a few people, few of the springers and IOP series who were indexed in Scopus, and at the same time some uh, journals as well, which are currently in the Scopus, which we are not aware. Yes, sir. Yes, sir. Yes, sir. I can hear you, sir. Yes, sir. Yes, sir. Yeah, yeah. Yes, sir. Yes, sir. We had the meeting, sir. Sir, sir. Now it is audible, sir. Yeah. Yes, sir. Yeah. Yes, sir. Yes, sir. Maybe a month before, a couple of months before, we had the meeting, and what we discussed that because some of the journals has been removed from the Scopus, so if you go with that one, then at the later stage we will have some issue. So, and then we thought to discuss with the Springer links where the proceedings will get published in wherever elsewhere or Procedia or something. Yes, sir. Yes, sir. So all of them have different payment modes and different operating modes as well. And IOP series, Institute of Physics, they are also now offering this conference hosting things. Yeah. Yes, sir. Yeah. So that was the discussion, sir, to initiate that one and to discuss with Springer or anyone who will guaranteed that it will be published in Scopus Index. That conference proceedings will publish in the Scopus proceedings. No, I can hear your voice, sir. Yeah. Ha. Yeah, one for the voice, and there is some issue. Yes, sir. Yeah, it is audible, sir. Yes, sir. So that was the thing, and then I had the discussion with the Prem, and he spoke to several publishers, Springer, IOP series, and with some conference, some journals as well, which are currently indexed in the Scopus. So that is the thing, sir. That is and the idea here is if we go with the Springer, I think it will take 2-3 months time from now because they take their own time. So maybe the Prem can elaborate on this aspect. Yeah, good afternoon, Prem. Good afternoon. I I think, sir, there is some delay. Some delay is there, sir. I think from your side, sir. Yeah, yes, sir.